E7. The equations for ionization energy and electron affinity, exo and endothermic. Okay, these are our Leo and Gur equations. And you will need to know these for several chapters as we get into bonding, and certainly as we get into redox, oxidation reduction. These are going to be very important. We have some trends on the periodic table, and we've looked at trends for atomic size and metallic character, which go this way. And I've had you draw these, so you know that things become more metallic in this corner and they're bigger in this corner. And then we have some trends that follow towards this upper right corner. And one of those is ionization energy, and another is electron affinity. The trend is the same, but the processes are different. And I'm just going to kind of cover a couple of these test-ins in one as I explain this part. The equation for ionization energy. We're looking at taking an atom, we would put in the symbol for any element, maybe sodium or whatever, and we add a certain amount of energy to it. That is the ionization energy. I'm just abbreviating it as IE. Each element has a specific amount of energy that it takes to remove its outermost electron. It takes even more to remove the next electron, and then so on and so on and so on. But often we look at just the first ionization energy. We add energy to the element, and that element turns into a positive ion. We add just the first ionization energy, it's going to be a +1 charge because we're taking away one electron. And we write that that one electron is nearby. Sometimes we don't write the 1, we just write E-. If 2 electrons are given off, then we would write 2 electrons, etc. So the atom plus energy forming a positive ion and an electron. This is an endothermic process. Endothermic, okay? We have to add heat. Heat goes in to make that happen. Energy has to be put in to strip away the electron from the outer shell of an atom. Now that's as opposed to the electron affinity. On the other side of the period, or up here in this upper right corner, we have elements that want to get more valence electrons. Our metals typically follow with this equation because they're okay with losing valence electrons. Our nonmetals in this upper right corner want to gain electrons. So in that case, we'd have the element, whether it's A, B, C, whatever, you know, fluorine, chlorine, whatever element we want to use, and that element takes in an electron, probably from that one. When that happens, it forms an ion with a -1 charge, and it gives off energy. And that energy is the electron affinity. Electron affinity. I'm not writing it all out because I know you've seen these definitions and sample equations. This process, exothermic, because the energy is on this side. So we have exothermic over here, endothermic for this one. There are a few elements on the table that will take another electron if we force them to. So there's an exception to this second equation. And another reason that I really want to point out these equations right here, right now, for those of you that are watching, is because this is an honors page question. And it's a couple honors page questions related to this. So for those of you who are always wondering about hints for the honors page, hello, right here. The other version of this is the atom plus the electron forming the -1 ion minus energy. And that's really the same as saying the atom plus the electron affinity energy forming the -1 ion. I kind of prefer this equation here, but the minor difference is the positive sign and negative sign on the product side of this equation, reaction equation. When we say and energy, we mean energy released. Because energy give is in the table is negative, that's how chemists and physicists record energy that is released. If it's the ion minus energy on this side, it's the same as saying energy going in over here. So this is an endothermic process. Endothermic. And that one is an exception. It only happens in column 2, the alkaline earth elements that have their s orbital filled, and to make them take one more electron, they'd have to create the p orbitals or use the p orbitals. They'd rather not do that because they're metals anyway. They'd rather lose electrons. And then the noble gases. Sometimes we can force a noble gas to take an additional electron, but of course that's not the preferred state for a noble gas because they already have their full outer shell. Okay, that was a long-winded explanation for test hint number 27, but like I said, I wanted to spend a little time on that because you will see this on the honors page. Actually, I'll see it because you're going to write all about it and explain it with examples when it comes to the honors page. Test hint number 28 says, the definitions of ionization energy, electron affinity, and electronegativity. You are sophomore and junior honor students at West Geauga High School. You can look up words. Get straight in your mind the differences between ionization energy and electron affinity, and then that general tendency towards attracting electrons in a bond, which is electronegativity. Look it up. 29, test hint number 29 is going to ask you, or test question number 29, is going to ask you to compare a couple elements in light of their ionization energy, electron affinity, or electronegativity. So it will be the degree. Maybe phosphorus compared to chlorine, or indium compared to iodine, something like that. You need to know for this question that the trend for ionization energy and electron affinity is that they increase in the upper right corner, the highest values. Means it takes the most energy to pull an electron away from an atom in these nonmetals, and conversely, the most energy is released in this upper right corner for these nonmetals when they gain that other electron, especially the halogens, and they fill up their outer shell. Okay? Those elements in the upper right corner have a stronger pull on the electrons in their shell. We know that from the trend in size as well. The pulling power of the nucleus, pulling those electrons in closer as we go across a row. Since they're held tighter, it means it's going to take more energy to remove an electron. They can also more easily grab another electron to fill up their shell. They release a lot of energy in the process. Alrighty, number 30 and 31 are the same hint, the trend for atomic radius applied to specific elements. The atomic radii increase to the lower left. So elements get bigger as you go down a column because you're adding energy levels, whole energy levels. You've been very good with this from what I've seen in class in our discussions. As you go across a row from left to right, they get smaller because, like John told us, they have that pulling power from the nucleus. We've got a greater effective nuclear charge as you move across a row because there are more protons. Take a look at your trendy periodic table inquiry activity as well. And the increased number of protons as we go across a given row within one energy level, there's pulling those outer electrons in and hugging them more tightly. Okay, and